All right, so I have the last talk for today with a few other speakers. I hope you're still all awake and are ready. Yeah, perfect. And ready for some war stories with the JVM. So I will talk a little bit more about lessons learned in Netty. So I'm not sure if everyone knows what Netty is. I hope so. If not, if you use the JVM, you probably use it somewhere. So chances are pretty high. So while this talk is about Netty, I think a lot of things that I'm talking about here is more generic, so it may be even helpful in your framework. So I hope you will enjoy it. All right, let's go. So we always have an about me slide. I will keep it short. So I'm the Netty project lead at the moment. I'm a Java champion, which means some people thought I'm very important for the Java system, ecosystem, for whatever reasons, mostly because I'm always complaining about Java NIO, I guess. I'm a Cassandra MVP, which means I did some contributions, some important contributions to Cassandra in the past. I'm a member of the Apache Software Foundation, which probably everyone knows here. And I'm usually working on large-scale network services or frameworks, which I used with them. So very shortly, what is Netty, just in case you don't know? So first off, it's a general purpose network framework. What does it mean? So it's not like a Jetty or whatever HTTP server. You can build something like this with Netty, but it's really more about you can build whatever network service or framework you want on top of it. So it's all about shoveling data around like bytes on the wire, basically. It's very low level. That means while the API, I think, is kind of easy to use, I have it as a last point as well, it's not as easy as you probably would have expected when you first come to Netty. Because honestly, network programming, it's not easy at all, right? To handle back pressure and all that kind of stuff. So it gives a lot of flexibility. So it's not as easy as, for example, Tomcat, Jetty, whatever. But you can do a lot of great things with that. It tries to hide many optimizations from the end user, which means you shouldn't care about it. What does it mean? So we do all kind of craziness, and I really mean craziness, to make it fast. We use unsafe, which you should never use. That's what I was told. So if you think you should use it, maybe you still can, but it's unsafe. That's the name. You can do all kind of crazy things with that. We do a lot of JNI because JNI is a lot of fun. So if you ever look into a project to write JNI, Netty is the one. We love contributions, by the way, right? So who uses Netty? It's always nice to tell someone what companies use Netty or what projects use it. So first off, just to be clear, the latest stable tree is 4.1. So we also have 4.0 and 3.0 and all of them, but 4.1 is the supported one. It's deployed and used almost everywhere. So if you're on the internet, you probably use Netty in some extent. So if you used, for example, Twitter, today you use Netty because Finagle used Netty, and Finagle is the core of Twitter, right? But it's also used by Alibaba, Amazon, Apple, eBay, Facebook, Google, Netflix, Twitter, Square, and so on and so on. So basically, all of the big companies are using it in some extent. If you are really interested into it and just like to, call out names, you can go on the website and check in. If your name is not there, just add it as well because we love to hear you use it. It's really successful in terms of API. It was even ported to different languages. So for example, it's ported to Swift. There's Swift NIO, which is the de facto standard if you write network non-blocking code in Swift these days. It was ported to C++ Wangle, which is a project of Facebook. So if you know Netty and know the JVM, but also know C++ and use Wangle, you can just go ahead because it's very, very similar. But there's also .Netty, which was done by Microsoft. So it's really, I would say the API is very, very generic, so you can implement it in different languages. And it's de facto the standard if you write network applications on the JVM. Even if you don't use it directly, you use it somehow, or most of them, right? Hopefully I'm not wrong with that. So if Netty 4.1 was so great, why we even need to care about the new version? This is a good question, right? Because if it works, don't touch it, so you don't break it. Well, the problem is, there's a lot of tech debt. I think that's the biggest problem that we have. So Netty 4.1 is there forever, basically. I think it was released like 8 years before, maybe 7, I don't remember exactly. And we are basically supporting it since forever. Which means we have some APIs which are just grown over the time. We have some APIs which are not as user-friendly as they should be, which we found out too late, as always, right? We would like to use usage of Java 8 features internally, which is a little bit of a problem because it's so old, we actually still supported Java 6 in the core. I don't hope you use Java 6, but there are people that still use Java 6, believe me. We want to refactor things not only in terms of the API, but also to make it more performant, because we made some choices which at the end were not good, and we only found out too late, right? And also we want to remove some obsolete code, because the best code is no code. All right, now with all these details, we go into the more interesting things, I would hope. So let me give you a deep dive into things that we learned in Netty 4.0 and 3.0, and that we plan to improve in 5.0, which may mean we have some API breakage, but we also already backported some of them. But I think they are quite interesting to understand. So first off, stack depth is pain. What does it mean? If you ever worked on a reactive framework, and if you did Scala, for example, and do a lot, like of futures and chain them together, if you have a stack trace, good luck. It's 100 lines of code, not code, like output, and you try to understand what's going on, and most of it is not really interesting, right? But there are other problems. So why does it even matter in Netty? So in Netty, we have the concept of a channel pipeline. I make it very quick here. The channel pipeline is basically the base abstraction of Netty. It just allows you to stack channel handlers, that's how we call it, behind each other or in front of each other, that basically intercept events and do something with them. The thing here is that, like we have these 3 channel handlers, so something comes from the wire, some bytes, for example, it goes into the red one does something with it or don't does anything with this, pass it to the next one, and so on and so on. So you can build up like basically chains of operations. And the same is true for outbound stuff if you want to write something, right? Which means that you end up with a lot of them. The problem here is that usually in real applications, you have like 4 to 12 of these handlers. Maybe you have even more. If you're super happy, you have less. And this means that because each channel handler basically passes the event to the next one in the pipeline until you basically have a terminating one, that you build up large chains. So as you see on the right side, it's probably too small to read, which means it's a bad sign. We end up with such deep frames that it's not only hard to debug, but also the problem is that by default, the JVM stops to inline at some point. By default, it's basically 9 line stacks or line methods. You can adjust this, but as always with all the different configuration things that you can do with a JVM, the best thing is if you don't need to touch it, because if you start to touch it, it has also other effects, right? So let us look at the channel handler. So that's a channel handler. It has a lot of different methods, basically. We are just talking about channel active here. So channel active is called once a new connection is established, right? If you're on a server, for example. And if you're interested in do something with it, you override this method, implement it. And if you're not, you basically call fire channel active, which passes to the next one. That's when you build up the chain, right? So because of this chain that we have, we thought like, okay, how can we improve this? How can we remove the chain? Because in reality, even if you have like 12 of these handlers, often you're only interested in one event and not like 12 different events that the channel handler provides you a way to extend. You may only be interested in channel active, but not in channel read, for example. So what we did was basically we came up with the idea, okay, why we don't introduce an annotation? The annotation itself, we put it on the default method, basically, and which means like if you don't implement anything, it basically is there. You cannot use it by yourself because we thought like, oh, it's pretty dangerous because you can shoot yourself in the foot, and you shouldn't need to use it. The thing here is the default channel pipeline, which holds all the channel handler, basically looks up, okay, I got a channel handler which is added to the channel pipeline, which methods are annotated with the skip annotation. If it detects there's a method which is annotated with this, it basically calculates, okay, this handler will never be interested in this event, so I shouldn't even call it at all. I should just skip it directly and go to the next one, which means we basically make the stack a lot, a lot smaller in size, which is kind of like we do some kind of a manual cheat, I would say, right? We just remove operations that we really don't need to. And how that looks like is like this. The implementation just, just the most important part. So we have the skip annotation. We have the static method, which basically just checks like, oh, is this handler type, does it have this annotation on it? Then we have this default implementation, which has the skip one that I told before. And then if you want to do something, you just implement it, override it, the skip annotation is not there anymore, right? And what you can see here, because everything is more interesting with numbers, is we did some benchmarks, and that's a really, really simple, stupid benchmark. So we basically have 5 channel handlers in the pipeline, and the last one is like the terminating one, which means like the first 4 could just skip everything, and did test how many operations we can do per second, basically. Without the skip annotation, we are about like 230,000 operations. If we have the skip annotation, we are up to about 750,000 probably, which means we are more than 3 times faster. And that's only for 5 handlers. So in real applications, like I said, you usually have 12, which means like it's a lot of overhead that we're basically crunching out. And these operations happen on each time you read something from the wire. So it happens really, really frequently. So these methods are super hot, right? So after we implemented this, we were like, okay, how we can even make this faster? Because faster is always good, right? So what we basically thought, like, okay, so why we don't cache the bit mask that we basically calculated, which basically methods we want to call, and just store it somewhere. So first off, we started with some concurrent hash map kind of thing and stored there. But the reality was that even if it's primarily read-only, it's not for free, right? And Netty has a model of an event loop. So basically we have like multiple events loop. One event loop is one thread. It always is powered by one thread, and this thread never changed. So what we said, like, okay, why we don't just cache it basically in a thread local, look it up there with a thread, and then use it, which basically means in the worst case you recalculate it like n times, like thread times, which is not too bad, right? Because it only happens once. Maybe just an interesting note here, we also have something which we call fast thread local. I'm not talking about this today, but basically it's an optimized version of thread local for our threading model, which is like 35% faster. So if you ever look into building your own thread local kind of type and you're pinned to one thread, you maybe want to check that out. So how to get this improvement? Well, I mean, first off, we only did it for Netty 5, but at the end we decided we can just backport it pretty easily to Netty 4.1, which means you get it for free. And we did this, and I think it was just added like 6 releases ago, which is basically 6 months ago, because we release like every month. And we saw like great improvements in performance in general by having the user not change the code at all. You get it for free, which I think it's always the best performance improvement, right? If you don't need to change anything. All right. We are going to the next. So like I said, Netty has an event loop. And the problem with Netty, this event loop is basically black magic. It's the core of it, and it's not extensible. What does it mean? So the event loop works like this. So you have this basically endless loop running forever. That's powered by one thread. It's waiting for I/O to happen. Once the I/O is there for a connection, we basically pick it up, process it, then also process like the user task that the user submitted to the event loop, and do it again and again until the application is basically shut down. So that's the whole concept, right? The problem here is that basically each of this event loop implementation is very specific to the operation system or to the transport, because how you select for I/O is specific to what you're using. In Linux, you use epoll, for example. In BSD or in macOS, you use KQ. In Windows, you use event ports, and so on and so on. And also, they are popping up more and more alternatives that you can use on different operation systems, like, for example, IO Ring, right, on Linux, which is like a new one. So we saw like it's actually a bad thing that it's very specific, right? Because the problem here is that even if you could adjust it and extend it to add some functionality, you would need to redo it every time you need to support another operation system. I mean, we're still supporting also NIO, which is basically Java kind of version, which works everywhere. But let me tell you this, we have our specialized transports which are written in JNI, they are a lot faster and produce a lot less garbage. Everyone is using that in production, basically, that I know that cares about scale. All right. And we even make it hard to extend them because most of them are final. Because why? Because we didn't want users to extend it and then depend on the implementation details. Because as a framework as Netty, which is used everywhere, once people start to extend your stuff, you cannot break it anymore, which is pretty bad. So why is this a problem? Well, so why is it a problem that you cannot extend it? Because you don't get information out of the event loop. Because what you usually do with something like a thread pool executor, which a lot of people extend, is you add metrics, for example. So you override methods to get a better idea how often is a runnable scheduled, how long did it take till it was scheduled to get picked up and run, how long did it take to run, to complete the run, and so on, how big are the queue sizes. And you want to make smart decisions about this, right? In production, you need this kind of insight, especially if things start to go wrong. I mean, as long as everything is fine, nobody cares about all this information. But as your service gets slower and slower, you want to understand, hey, is anyone maybe blocking my event loop? And so no process can be made. Or is one event loop more busy than the other one because more connections are on them? Or is more I/O going on? Or is it specific to a protocol? And all this kind of different information. That's usually what people want to have in production kind of systems, right? So how can we fix this? So the very, very sad news is in Netty 4.1 we cannot fix it at all, or we would need to break it, which we can't. So what we did in Netty 5, and I think that's one of the features I'm most excited about, even if it sounds maybe boring because it gives you so much more insight into what is going on at the end, is basically, you saw before how it works in Netty 4.0. What we did in Netty 5, we basically broke up the responsibility of executing tasks or executing operations and selecting from the I/O, from the operation system. So we basically have now two components in the system. One is responsible to select all the events, and the other one is basically responsible to do something with the events. So that's on the right side, right? So how does it look from an API perspective? So we have this event loop. Like I said, the event loop is basically the thing that drives everything. We have an inner interface which we call unsafe. Why we call it unsafe? Because we don't expect users to call it. It's more for us. If you call it, good luck. You can do it, but don't blame us, right? That's why we call it unsafe. It's basically, it's a sign to don't touch it. Then we have this I/O handler, which basically extends this unsafe interface, and this has different methods. Like, I want to run something, and run means I want to run some native code to select I/O, basically. I want to wake up if I'm blocking in native code. I want to prepare my native stuff to be destroyed, and I want to destroy it at the end, right? And this context that we basically give in can tell you something so you can make smart decision. Can I block? Can I not block? How long I can block? Or what is the maximum amount of time I should expect before something happens, basically. So coming back again. So we talked about why is this a problem. So let us look now how the API looks like. So before you basically had these event loop groups and you basically created them and you had one of the event loop group implementations per operation system or per, like method how you select the I/O. So you created something like new NIO event loop group, new ePOL event loop group, and so on and so on. So now what you're doing is to just create the multi-thread event loop group and pass in basically an I/O handler, which is specific for the operation system that you are doing. And everything else just stays the same. And which means that basically we are strongly encourage extending this multi-thread event loop group, which returns single thread event loops, basically, because then you can follow on the pattern of thread pool executor and get information out of it and customize it and do a lot of different things, which also comes with the idea implement once, use it multiple times, so you don't need to duplicate code all the time. So what extension points we're providing now? So for example, we allow you to override the run method. The run method is basically the one that is called once and that runs the endless loop until we shut down. So what you can do with that? Well, you could set up thread-specific informations, like a thread local or whatever you want to do. We do have a method run IO that you can override, which is called basically each time we run some IO that we know of. And basically, it returns how many IO events it processed. So you can have metrics like, okay, the last time I called this, I basically processed 100 different connections, and the other time 1,000, and so on and so on. And it makes it interesting to make smart decisions which event loop to use the next time. We allow you to override register and deregister, which helps you to keep track how many active connections are sitting on the event loop, and so on and so on. So there's a lot of interesting things that you can do with that. And this one basically extends the single thread event executor, which also gives you a lot of extension points, which also follows basically the abstract execution service in Java. So you also have like new task 4 that you can override, so you can return your own promises, you can wrap your own tasks to do something like metrics and all that kind of thing. So I think it's a lot more extensible than before. So what can this be used for? Like I said, smart event loop selection based on the load, for example, or the number of registered channels, reporting when event loop tasks take too long or longer than expected, so maybe some kind of a watchdog that you usually know from blocking code, right? Or you can preserve context of task executions, a little bit like a thread local, but it hops with execution of the callbacks, right? Which you usually need in your frameworks. All right. So now we're coming to a very interesting topic. So in Netty, we have a pooled bypass allocator. I will talk a little bit about this and why we have it, and why this was not enough, basically, for us. Because we still had a lot of GC pressure, which is bad. So we have this pooled bypass allocator, and it's basically implemented after jmalloc. I'm not sure if everyone is familiar with jmalloc. So the J doesn't stand for Java. It stands for JSON. It's the guy that invented it, he works for Facebook, and that's his malloc implementation. And I think it's even the default in FreeBSD, or it was at some point. But you can flip it in if you like to. You can compile it and replace a glibc or whatever you have, like a glibc malloc, and use it. And the idea here is that basically to make allocations cheap, you have arena-based allocations. So the idea here is you have multiple threads, right? And these threads, each time you want to allocate some bytes, you look up first in the cache, which is thread local, which means like if there's something inside there, you can basically allocate it without taking any logs. So that's the best case. If there's nothing there, okay, so we must lead to look somewhere else. So we look into an arena. The arena itself is like a mini allocator, I would say. And usually an arena is shared with multiple threads, which means like this, all of these threads access it at the same time, which means there needs to be some synchronization going on, right? But because the implementation is kind of smart, or the idea of the implementation is kind of smart, they even minimize the allocation, the synchronization on the allocations here, because how it works is you have these arenas, and you may end up with 2 different threads or 3 or whatever in the same arena, but the arena itself is basically chunked in size classes. What does that mean? So if you do an allocation, which is 8 bytes, for example, we have the size class which goes from 0 to 64 bytes. So each allocation which is smaller than 64 goes into this bucket. Then we have 64 to 128, 128 to 512, and so on and so on and so on, and it's even configurable, so it's not a fixed thing. And that means like if you're allocating for multiple threads and you allocate for different size classes, there's no condition going on, right? Because you basically log or synchronize on these size classes. So it's already really optimized. It's really cool, like the whole idea. And we re-implemented it in Java, basically. So what we pool? Well, we pool direct memory because first off, direct memory is actually expensive to allocate and deallocate. It's actually pretty bad, if you ask me, because basically the bound of the direct memory is tied to an extra setting, which is max direct memory, and the default is actually to use the same bounds as for heap memory. So you basically end up with 2 bounds, which are kind of unrelated anyway. So most people don't know that. So you end up with this kind of stuff. And the problem here is that's even worse because Java wants to give you the impression that you can allocate whatever you want and you don't need to care about freeing this memory because we are no C programmers, is that the garbage collector also needs to take care of your direct memory. But remember, it's allocated from direct memory, so it has nothing to do with the heap here. Which means like, how does it work? Well, they pull off a trick basically. So each time, like they do like a garbage collection, a heap garbage collection, they also free up direct memory. But if you only allocate direct, they will never run a GC cycle. So how does it work? Well, there is a neat trick which is really scary. So if you don't believe me, you can look in the source code. It's OpenJDK, so it's free. You can look inside there. So what they do is, if you allocate a direct memory and there's no memory left, they say like, okay, cool. let us just call system GC and do a sleep for 100 milliseconds. And then we try again. And we do it a few times. We are maybe lucky, get memory back, everything is cool, everything goes on, or we do out of memory error. The problem here is, if you ask me, is that basically, if you're very unlucky, you will always be able to just allocate enough one time to end up in exactly the same situation again, which means like it's basically, you get a lot of latency, you get, stop the world kind of thing of effects, and it's very hard to debug. You don't want to have this kind of thing. I would prefer to just die, like drop it on the floor, out of memory, done. Don't sleep, done, right? But we also pull for heap memory. You may ask why, because heap memory is basically only like a byte array allocation and you basically wrap it. Well, kind of. The problem is because of the spec of how Java is specified is it always expects that it gets a memset byte array, which means the byte array needs to be filled with zeros. Which means like if you allocate huge byte arrays, basically, you always pay the price for memset, all of them. And it's not for free, basically. So here I'm staying, say like, it's kind of useless for something like Netty, which puts a container around your bytes anyway, which disallow you to read more than what you wrote in before, right? So you have like writer and reader indexes, and we kind of already, like restrict you what you can do. So why we should memset? Some people may say, okay, because of security reasons, we want to override what's inside there, but I think that's a weak argument, because at the end, if you take a heap dump, you have it anyway, because it sits there until it's garbage collected. So I don't buy that. So we do this. And we even go more on with Netty. So if you use Java 9 and later and open up some access to some internal unsafe, so there are now 2 unsafe basically, we can even allocate byte arrays which are not memset at all because they have an API for it, right? But people should not use it, but we do anyway, right? So, okay, we have all this pooling, everything is cool, so why is there still a problem? Well, the problem is because Netty uses a byte buff, and the byte buff is a concept of Netty, and you want to talk to the JVM or to the JDK libraries, they expect a byte buffer, which is their thing, basically. So we need to basically adapt from a byte buff to a byte buffer. The thing here is we don't do any copy of the storage itself, but we still need to allocate the object. And if people tell me like that's not a big problem, then they probably didn't push the system hard enough, because if you start to allocate a ton of objects and you need to garbage collect, it basically steals your CPU. And there are always problems, right? So let us just look at the benchmark. So the benchmark is very stupid. Basically, it's just an echo server. So we send some data in and we basically echo it back to the remote peer. And what we found out is that it's basically allocation free mostly in a steady state, except the byte buffers, right? You see it. It's marked red. I'm not sure if you can read the number. It doesn't matter too much, but it was basically the most expensive allocation, or the most objects that were allocated. And we said like, okay, cool. So what can we do about this? Because we already pool the rest of it, right? So we came up with the idea why we don't actually also cache these byte buffers. Because, we allocate this chunk of memory and it's sitting in a pool, and there, it will never change, and if it changed, basically we drop everything anyway. We can just reuse a byte buffer as long as we make sure that they are not in use anymore. And in Netty, we use this concept of reference counting, which is kind of scary because now you're back in C-land, basically, right? So in Netty, you need to call release to release a byte buffer. And if you don't do, that's bad, because we use a pool. We have a leak detector which uses like very interesting implementation. So if you're into like details, so we use like weak references and sampling to understand if if there's still a reference to this and no reference to it and you didn't call release. So it's very interesting, but it's very specific, right? So what we did was we added this DQ, and we basically we just put in buffers inside there once we return them and pull from them and basically reuse the buffers. And the interesting thing here is that once we did this, the allocations are basically gone. So now we basically only allocate like, I don't know, something like 1,000 objects basically for the whole run. And it's basically stay like this forever. As long, when a new connection comes in, we need to allocate again. But still, it's a very good improvement, right? So Netty 5, let me just talk very briefly about the roadmap because we are pretty short in time anyway. So Netty 5 is planned for 2020. Depending on how many external contributions we get, it goes faster or slower. So if you're bored, or if you just like Netty, or you just, I don't know, want to do something cool, you can contribute. It's open source. We love contributions. We love PR reviews. It's open source, right? We want to do like beta and alpha releases very soon. We have a GitHub project where we track the progress of the whole thing. There's still a lot to do, sadly, like always. And now is also the idea to bring up new ideas and concerns, because we can still break stuff. Once we are done with Netty 5, we will need to wait for Netty 6 again, right? Which I don't know when it will happen anyway. So what did we complete? We simplified the channel handler abstraction already. So before we had, because we were Java 6, we had all these different abstract classes and adapters. Now it's just on one interface anymore because we have default methods, we have skip annotations, so it's not a problem. We did the event loop stuff, the extensibility that I talked about. We provide a way to adapt futures. We have our own futures and convert them to completion stage. We removed a lot of deprecated stuff. We dropped Speedy. I don't hope you use Speedy. You should use HTTP2 instead, and all this kind of stuff, right? Planned work, rework HTTP2 a little bit, rework our cookie stuff because there are changes that we would like to do. We want to support TLS 1.3 early data, so we already support TLS 1.3. So even if you use Java 8 and you use our stuff, and we also have a native implementation of SSL using JNI because we love the pain, you get TLS 1.3 for free. You should do it. It's pretty cool, actually. We want to rework the channel lifecycles and just clean up in general, right? All right, so I'm almost done. Last slide, or almost last slide. Like I said, we love contributions, so go nuts. I want to see 1,000 PRs today, so I will try to review them all if you do it. We have Stack Overflow, mailing list, IRC channel. We own GitHub, Apache license too. So basically you can do whatever you want with a project. You can do commercial stuff, you can sell it, whatever. So you can, it's a very, very, I think, very, very good open source license because it doesn't have a lot of restrictions. You just need to do some attributions, basically. All right, so I'm basically done. If you have any questions, I'm happy to answer, but I'm also happy to answer later if you're shy. Or if you have no questions, that's fine as well. Anyone?
What kind of Java 8 features do you want to use, or do you? What was the motivation basically for Java 8 features in 85?
Okay, so you're asking why we even need Java 8, right? What features we are looking for to use? So there are a few. Method handles, I think is one of them. So at the moment we have some kind of runtime checks sometimes to decide, which is basically usually optimized away by the JIT anyway. Then because the other code is dead, right? So we have some checks like so we take the Java version and then based on the Java version we do something depending on which version you run. So we do some stuff for Java 11 because there were some APIs, for example, that was added there, or we do something for Java 8 if there's something, and so on and so on. So we would like to remove all these hacks basically and just use method handles, which are also a lot faster than reflection. So at the start, we actually talked about make Java 11 the minimum. But once we started, we basically realized there's no real pressing need to be Java 11, and there's still a lot of people on Java 8, right? And it's a very low-level API, which means like if you use it, we put the burden on the user, I would say. I mean, I think it's fine for a service, but for a library, you should try to stay old, I would say. But yeah, it's basically more about, like method handles, some, like some new constructs that we can use internally. We have a lot of hacks in the SSL engine, for example, because we want to make it work with Java 6, 7, 8, 9, 11, because there are different features like SNI, matchers and all that kind of stuff. And also like Java 8 is nice because, so a lot of people use completion stage, for example, and we are now allowed to, like convert to it. So you can, like use your functional programming kind of thing. Yep. Does that answer your question? Okay, cool.
Thank you very much for the talk. It was a whirlwind of low-level JVM stuff, and it was very cool.
Thank you.
I had a question about, and I saw the YourKit little waterfall thing going down there. How did you discover a lot of these performance bottlenecks?
Yes, that's a good question. So usually, I only use YourKit here because it's easy to show, actually. So I'm not using YourKit too much, actually. So I'm a big fan of Async Profiler, for example. I'm not sure, are you aware of Async Profiler? It's an open source tool, it's pretty cool. If you need more information later, I can also give it to you. But basically, Async Profiler, it allows you at least, so on different operation system, you can do different things, but you can basically do allocation profiling, like CPU-based. You can also do like log stuff. And for example, on Linux, it allows you to basically have a full view of the system because you see the Java stuff, but you also see C and even like kernel stacks. So you get like a full-blown picture, which is especially interesting for I/O stuff or SSL or whatever. So you get like a good understanding, and it's very low overhead. It's really very low overhead. So you can actually run it on production system, and you don't need to have an agent and nothing. It just basically works, right? So it's I think it's a pretty cool project, for example. Or you can also use like perfmap, for example, which is another one. But you can also export the data in flame graphs, which help. So yep. And also customers, basically like internal customers that tell like, oh, this is slow, right? And then you look into it, or like open source project, right? You know what I mean? It's yeah.
We have time for one more question.
Hi, Grace. May I ask, could you talk a bit more about the H2 rework and what's the plan for that?
Okay, yeah, so I will try to make it quick. So we have basically 3 APIs for H2 for various reasons. So we started with one API because we wanted to do it to make less allocations and all that kind of stuff. The problem with this API is basically that that it's very verbose and it's very un-Netty-like. So it doesn't use channel handlers, so you get like callbacks. It's very unnatural, and also it only works from the event loop, so it's very hard to use, I would say. And it's very wide, the API. So to fix this, basically, I think Twitter contributed another one, which basically makes, it used the old API, but create out of the different HTTP frames, it creates basically poachers and fires through the pipeline, so it's really Netty-like, right? But that still is kind of only solving it half, because now you have all the different frames, but they belong to different streams because it's multiplexed. And now we have the third one, which builds on the other two, basically, which multiplex these frames. What does that mean? Actually, we're creating a new channel with a new channel pipeline per frame, per stream, which means like for you, it just looks like a channel, like a connection, and you can add whatever channel handlers you want to, and they work the same way as Netty, but they are specific to a stream ID, which means like it's only the flow for the stream, like the frames. And we actually only want to have the frame one and the multiplex one, because you not always need the multiplex one because it has some overhead, but the frame one you need always. But we want to remove the first one, basically.
Thank you.
All right. Then thanks a lot, and enjoy the night and evening.